and get rid of the pictures here. Okay, so I want to start by seeing if there were any questions that you would like to go through on the Newton's method. The screen you're looking at, shows the formula we were supposed to use to, let me just translate that again to find the, let me grab my marker here. Nope, it's not wanting to do it. So anyway, to find the next number, you take the last number and you subtract this ratio of the function at your first estimate divided by the derivative at your last estimate. And then what happens is you get a new, so when you do it the first time, like we did in class, you get this, we started with 1. This is our new estimate after you do the subtraction. Then we take the new estimate, put it over here, and then we get our next estimate, etc. And you just keep this process of recycling is called iteration. Did anyone want to look at any of those, or is there any question regarding that process? So I'd like to just follow up. I think it was Michaela that asked last time during class, what would you do on a test regarding this? Well, if this depends on I'm not going to have you do, 12 steps manually. Here, I guess we did it in 5 steps, but still that to me is taking too much time on a test. However, I need you to understand this formula, and maybe how do you take your answer and plug it, and use that new estimate and then go on. Just something in general about that process I might ask about. I don't know. It seems like there's never enough time to ask about all the things that are on a test. But hi, Jen. So again, let me just ask, does anybody have any any questions on the Newton's assignment? Were you able to make use of the spreadsheet template? This one I'm looking for a response for. You can chat it if you want, but were you guys able to download the template and make use of it? And did you get how to copy the stuff down? And I know that may have been a little bit confusing. Okay, good. Thanks, Richard. How about Michaela or Jen or Skylar?
Yeah, I figured it out. It took me a little bit, but I figured it out.
Okay, and I see Skylar's good. All right. All right, then I suppose what you're saying to me is let's get to the chapter review. And that's fine. Okay, so here we go with the beginning of our chapter 3 review. So first of all, I just listed the lessons, and we never did take lesson 3.6. That's why if you look on the screen, I have crossed that out. Likewise, there are some problem-solving problems way at the end. Those are not included. So everything except 3.6 is pretty much what we're doing. Okay. So, we've got this. This is in your book in several places. This is a summary of the types of derivatives we should now have available to us. Whoops, sorry about, I don't know why that is automatically jumping like that, but so this is what supposedly the quiz was supposed to be on. Of course, I didn't ask about all of this, but I guess I'll just remind you that this is a great reference point to go back to. Okay. So if you look at in the review, the first 4 questions ask you to find a derivative of the function using the limit process. So that's where you have to know your difference quotient. That's this thing right here. You know, you all have to know the difference quotient, f of x plus h minus f of x all over h. And then you need to take the limit of all of that as h approaches 0. So this happened right in the beginning, and it's the very foundation for what a derivative is. So I can say without a doubt this will be on, you know, something like this will be on the test. So if we take this example, let's take number 3 here for an example. So we need to find f of x plus h so that we can plug it into this difference quotient. So you take x plus h, plug it in wherever there was an x in the equation. You know, we got x squared, so now we need to do x plus h squared minus 4x, so we need to do negative 4 times x plus h. Anyway, we have to work that out, which gives us this line. And then I like this vertical format. From that, you have to subtract the original function, negative f of x. So right below it, I put minus parentheses x squared minus 4x plus 5. And I lined them up underneath the like terms. And then you can see that when after you subtract, you're going to get, you know, what's left there, 2xh plus h squared minus 4h, and then we still have to do this over h, and now take the limit. Well, we can't, because h can't be 0. But you can see, and this is fairly typical, there's an h that can be factored out of the top, which nicely cancels with the h on the bottom. Now, now we're sitting right here, and that, of course, we can take the limit of. As h approaches 0, it'll go away. We'll just have 2x minus 4. So, for sure, you guys, you haven't done this for a while, so you really should review this, okay? This is very, very important. Any question on that? We'll also take a look at number 4, which, of course, has a quotient in it. So here's number 4. Once again, we need to do this limit as h approaches, you know, this thing in the box here. The difference quotient and the limit as h approaches 0. So 6 over x could be written this way as 6x to the negative 1. We need to take the derivative of that. We can use the power rule. I mean, that's the shortcut. Okay, so how do we do it using the limit process? Well, we've got to find f of x plus h. So that's just 6 over x plus h. Just plug in an x plus h where there's an x. Subtract the original. So that's the blue on the numerator here. Okay, and then that's all over h, the limit. So obviously, we've got to do something with this 2 fraction subtraction on the top, and you can see what I did in black, I think, and that is I need to get a common denominator, so I multiplied this one by x over x and this one by x over h plus x over h, and then that gives me, you know, now I have the common denominator x times x plus h, and now I can literally subtract the top. So, I mean, x times 6 is 6x. That's this one right here. That's that one. And then we have minus 6 times the quantity x plus h. So it's negative 6xh minus 6, negative 6x minus 6h. So that's the rest of that. Okay, now we can what? We have one fraction divided by, you could think of h over 1 instead of just h, and now we could divide fractions, invert, multiply, and the h nicely goes away. Now can we take a limit as h approaches 0? Even though there's an h in the denominator, we can, because what will happen as h approaches 0 is you'll just get x times x down here. And then, okay, this is not part of the problem, but if you look over here at the right, we could have done this by the power rule. We'd have got negative 6x to the negative 2. And what does that mean? It means x squared on the bottom, and sure enough, that's exactly what we got. So let me remind you that when you do this limit process, you should get obviously the same answer that you can get by any of the shortcuts we have learned. All right, let's take a look at numbers 7 and 8. This is the way they are in the review. It says, describe the x values at which f is differentiable. So here you have to remember that functions are not always differentiable. And you remember the things you can't do? You know, like in number 7, when there's a cusp, you can't find a derivative at that point. So where is number 7 differentiable? Any place else. So from negative infinity all the way up to 3, and from 3 all the way up to positive. Just all we're doing is excluding that 3 point. Likewise, number 8, another thing you cannot differentiate a function on is, well, when it doesn't exist. Like we have a vertical asymptote on that function at x equals -1. You cannot differentiate it there. So where can it be differentiated? Basically everywhere else. Interval notation tells us that we would write that as the interval from negative infinity up to -1 and from -1 up to positive infinity. Stop me anytime with questions. Okay, let's look at the next section on the review, finding a derivative. And here we can use the rules that we have learned in chapter 3. So number 13, well, I guess I did number 15. So let's take a look at number 15. That's this one on the top here. Let's see. I don't know why my pen, hang on, I'm going to just do a little pen check here. Pen's not working. Okay, we'll see if we have something now. There we go. So this is number 15 here. And you can see I rewrote it. Up here it says 2 over 3t squared. Does everybody see that this is the same thing? I got the constant out of there, 2/3, because you know that when you take the derivative of a constant, you kind of bypass. You don't do anything. You just leave the constant be alone. And then 1 over t squared I wrote as t to the -2. Okay. Well, now we can differentiate using the power rule. -2 times 2/3 would be -4/3. Reduce the power by 1. And then, okay, now the only problem is we shouldn't leave that negative exponent. And so you can just put t cubed on the bottom. Done. Likewise, number 20. Number 20, 5/3 sine s minus 2e to the s. Okay. So what's a 5/3 we don't do anything with. What's the derivative of the sine of s? Cosine of s. And what's the derivative of negative 2 to the s? Well, I mean, actually we should do, don't automatically think that there's no change. What you need to think of is that's really the product rule, isn't it? It's negative 2 multiplied by e to the s power. And you really need to do the product rule. So you do the first times the derivative of the second. Need to get a little space here. Plus the second times the derivative of the first. That's a 0 there. So that wipes itself out, and it really does come out. So anyway, just don't automatically assume there's nothing there, because it's sometimes you're going to have a sign change. So you need to check those things out. Okay, that's number 20. Questions, anybody? Please speak up if you do. All right. Let's go to this section in the book, finding the slope of a graph. Well, as you know, derivatives give you the instantaneous slope of a graph. So really, what's the only difference here? Well, you can go ahead and use your rules to find the derivative, but then they give you a point, and that's the point. They want the slope of the tangent line. So I've maybe messed this up by circling it, but in number 23, the function is 2x to the 4th minus 8. The point is 0, comma, negative 8, and it's that x value of 0 that I've circled. So what's the derivative? Easy. Derivative rule, power rule. 4x cubed times 2 is 8x cubed minus a constant, nothing. So here is our general derivative. And then our specific derivative, what's f prime at 0? And you can see it's going to be 0. So in other words, there's a horizontal tangent there. Number 24, shortcut. What's the derivative of this? Well, derivative of the cosine is minus the sine, so that would be negative 3 sine theta. And the derivative of negative 2 theta is negative 2. So there's your general derivative. Now, again, make it specific. Do it at the point 0, 3. What's f prime at 0? And here's where your trig comes in. The sine, what's the sine of 0? That's the height. You know, sine is a height guy, and that would be of 0 height when you're full length to the right. So negative 3 times 0 is 0, and you just get negative 2. All right, let's take a look at number 25. Yeah, this is the kind of word problem I might give you on the test. I mean, it's not major. There's not a lot of translating that needs to take place here, but anyway, volume, the surface area of a cube with sides of length s. Oh, that's not the one I did. I apologize. I did number 25. I circled 20. That's interesting. I circled 26, but I did 25. When a guitar string is plucked, it vibrates with a frequency of f equals 200 times the square root of t. F is measured in vibrations per second. Tension T is measured in pounds. Find the rates of change when t equals 4, and in part B, when t equals 9. So how do we do this? Well, we've got an equation, f equals 200 times the square root of t, and they're talking about time here. So this is one of those implicit problems where we have to differentiate the whole thing with respect to time. Okay, so we differentiate f with respect to time, df dt. Here we can do the power rule. 1/2 times 200 is 100. Reduce power by 1, t to the negative 1/2. Okay, hang on a second. So first of all, when you take, I don't know why I made a mistake here, but when you take the power rule here, when you plug in, okay, hang on a second. What did I do here? I plugged in t equals 4. Oh yeah, and this is t to the negative 1/2, which means it's a square root on the bottom, right? So this is really, I should have really rewritten this. It's to clarify it, that's equal to 100 over t to the 1/2, like that. That's the translation of that. And in the case when t equals 4, this would be 100 over the square root of 4, and 100 over 2 is 50. So like I said, this should be 50 here. And I really didn't need to do d capital T over dt, because this was, we were supposed to, I mean, t, there is only one t here, and so we didn't really have to do that, because that's what we were differentiating with respect to. So, I mean, that's not really clear. But the first answer is 50. And then when you do the second part, you're going to plug in t equals 9 here. The square root of 9 is 3, and 100 over 3 is 33 1/3. So those would be the answers to 25. Now let's do the 26. Okay, another implicit problem. The surface area of a cube with the sides being length small s is given by this. I mean, there are 6 sides to a cube, and each side is simply s by s. So s squared 6 times, 6s squared. Find the rates of change of the surface area with respect to s when s equals 3. So they're telling you to differentiate with respect to s. Okay? And that's small s. Now, it can be a little confusing. So I'm differentiating both sides with respect to small s. So on the left, we have to do ds, d capital S over d small s. And on the right side, we're using small s, so we don't have to do the chain rule, just a power rule, 12s. And when small s equals 3, 12 times, I mean, that one's pretty easy. And when small s equals 5, it's just going to be 60, 12 times 5. So that was a pretty easy implicit problem. Okay, now let's take a look at this one, number 27, vertical motion. Okay, so vertical motion is always based on gravity, and anything that is affected by gravity basically is going to behave in a quadratic. Why is that? Gravity is simply a quadratic function. That is, if you plotted something, it's going to be an upside down parabola. That's the way gravity works. So if you look at this equation that they give you here, you'll see it's got negative 16t squared plus the initial velocity times time plus the initial height s0. So v0 stands for the velocity at the when it was first shot, and s0 is the height it was. So if it was shot from the top of a building, then you'd have to have S0 be the height of the building, etc. Why is it -6? Why is this negative? Because it's gravity and it's always pulling downward. So whenever you're dealing with physics of a falling object, it's always going to have that negative something t squared. And if it's in feet per second, it's -16. And if it's in meters per second, it's a little different value, but it's the same problem every time. All right, so number 27, it says a ball is thrown straight down from the top of a 600-foot building. Okay, so 600 is S0. And its initial velocity is -30 feet per second. So now we can plug in V0 and S0. So the equation would be -16 t squared minus 30t, because the initial velocity was -30, plus, this is 600 here. I know it's hard to read. Okay. So what are we supposed to do? Well, we already did part A. Determine the position and velocity. So this is the position. Sorry, I'm running out of colors here. So this is the position function. Okay. Then it says find the velocity functions. Well, how do you get the velocity from the position? You take the first derivative. So what's the derivative of -16t squared minus 30t plus 600? Power rule, -32t minus 30. That's the velocity. Okay? So that's part A. Now, part B, determine the average velocity. Okay. Do you remember how to calculate average velocity? It's basically just a slope. You need to get two ordered pairs. So, and here's the interval we're supposed to do it over, 1, 3. So what is the height of the ball at 1? Just go back to the equation. If you plug in a 1, -16 times 1 squared is, -6. You can just plug it in and subtract, and then -30 times 1 plus 600, and you're going to get 554 feet. So here's our first ordered pair. At 3, the second part of the interval, plug in 3 into this equation up here. And what do you get? That time you're going to get 366. So what's the average velocity? It's simply the slope of these 2 points. You can see I carried that out right there. I took one y-coordinate minus the other, so I call this point 2 and this point 1 y2 minus y1 over x2 minus x1. Doesn't matter which point you call 2 and which you call 1, as long as you stick with it. So anyway, there it is, -189 over 2. Actually, is that 188 over 2? Yeah, I'm sorry. That's 188 over 2. And 188 over 2, we can do better than that, is what? 94? That's the average velocity over that interval. And it's negative. Negative over positive is a negative. So it averaged heading downward at 94 feet per second. Okay, back to part C. Find the instantaneous velocities when t equals 1 and t equals 3. Now, instead of using slope, instantaneous velocity, that's your derivative. So now, what's the derivative? We already figured it out. It's right there. It's circled in blue up here. Okay, so what's f prime at 1? -32 times 1 is -32. -32 minus 30, -62. Down there. And then what's f prime at 3? Negative 96 minus 30, negative 126. The last question says, what's the last part? Oh, no, I'm sorry, part D. Find the time required for the ball to reach the ground. Okay. Well, when it reaches the ground, what will be true of the equation? If you go back to this original height function, f of t equals negative 16, you know, this one right here. If you take that original equation, f of t minus 16t squared minus 30t plus 600, it's when it comes out to a height of 0. So you would set that equal to 0. Okay, I don't know. I did not do that up here, but let's do it. Okay, so negative 16 t squared minus 30t plus 600, and we'll set it equal to 0, because when it hits the ground, the position will be 0 feet off the ground. Okay? So how do you solve a quadratic? Well, we could try factoring it when it's set equal to 0. We can take what? A 2 out of that for sure. Divide both sides by 2. Negative 8t squared minus 15t plus 300. Can't really do any more factoring. How do you solve a quadratic equal to 0? We could try factoring it. You know, we could try doing, or you could use the quadratic formula. Right? Remember the good old quadratic? X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And then that would give you how much time it took. That will give you the number of seconds it takes to hit the ground. And once you know the number of seconds it takes, let me shift back to so I can see it. Then, if you know how many seconds it takes, that's the answer to D. Find the time it takes for the ball to reach the ground. And when you know the number of seconds it takes, can you answer E? What's the velocity of the ball right when it hits the ground? Well, you just figured out the time, so can't you just do F prime at that time? And then you'd have it. Okay, well, anyway, that's the kind of a problem maybe you're going to need to focus on a little bit, but that's got multiple parts to it, and it's, anyway, that's pretty important. Any follow-up questions there? I know that screen is full. Okay, let's go to number 33. Find the derivative. So this is just straight find the derivative. Okay, so here's number 33. We've got this function x squared plus x minus 1 all over x squared minus 1. Obviously, well, guess what? I avoided, so I guess you could say this is one way to do it. I wrote divided by the division of x by x squared minus 1 is, I wrote it as x squared minus 1 to the negative 1 power. Doing that allows me to use the product rule, which is a little less messy than the quotient rule. So one more time, I rewrote this like this. So x squared minus 1 to the negative 1 describes that x squared minus 1 in the denominator. Now, all right, I can use the product rule. The first times the derivative of the second. Okay, what's the derivative of x squared minus 1 to the negative 1? Well, negative 1 multiplied by x squared minus 1 to the negative 2. Chain rule. Okay, so there's the first part of the product rule, plus the second times the derivative of the first factor. Derivative of x squared plus x minus. Okay, so that's fine. Now, unfortunately, we do have a couple negative exponents, so now we got to come out. Now we got to write the ratios, right? So this first thing, which is right here, all is written as one term, right? There's a 2x on the top. There's a negative, so that's out there. You still got this x squared plus x minus 1, and this x squared minus 1 to the negative 2 becomes your denominator here. X squared minus 1 to the second power. And the second term, which is over on the right here, has 2x plus 1 on the top, and it's got 1x squared minus 1 on the bottom. Okay, this is crying out to be combined, in case you haven't been seen that in past problems. I mean, all I need is another x squared minus 1 on the bottom in order to get a common denominator. So let's multiply top and bottom by x squared minus 1. Now I have a common denominator of x squared minus 1 squared. Multiply this top out. Multiply this top out. You can see that a bunch of things eliminate each other. All I have left on top is what? Negative 2x. I've got negative 1x squared minus 1. And we've arrived at. By the way, can you factor this further? Do you really have x squared minus 1 on the top? And therefore you could cancel one of the two on the bottom? No, because that's not just an x squared minus 1, it's negative x squared minus 1. I can't, if I factored a negative 1 out of the top, then I would have negative 1 times the quantity x squared plus 1. Yeah, just can't go another step there. So let's take a look also on this particular section of the problems. Let's take a look at number 39. So here's number 39. So we've got 4x e to the x minus cotangent x. How do you take the derivative of 4x e to the x? Well, that's really a product rule, right? I mean, here, there's a lot. I mean, it's not showing the detail there. So really what you're saying is that's a 4x multiplied by an e to the x. And so when you take the derivative, it's a product rule. You've got the first times the derivative of the second, the derivative of e to the x is that, plus the second times the derivative of the first. So you see how, sorry for the sloppiness, so you see how we get these two terms as a result? 4e to the x plus 4 times e to the x. You see where this term comes from? Anyway, and then the derivative of the cotangent is minus the cosecant squared. If you can't remember that, you may have to use your quotient rule. Because remember, cotangent is cosine over sine. Anyway, when you're subtracting a negative, it becomes a positive. So there's actually a fair amount involved there on number 39. Questions? Next group is 41 to 44 in the book, and it's we're back to not just find the derivative, but find the equation of the tangent line at the point. So you'll notice on this section, they've got these points. So they give you a function and then they give you a point. So you find the derivative, the general derivative, and then you find the derivative at the point. So let's take a look at number 40. I guess I've got 44 down here. Okay. So 44, we got to do a quotient rule, right? Denominator times derivative of numerator. The derivative of the numerator is 0 minus, yeah, so it's just minus sign, minus the numerator times the derivative of the denominator, all over denominator squared. Okay. So, I mean, that's it. Anyway, we might as well go right to the substitution. So what's the derivative at that x value right there, pi over 2? So trig again. What's the cosine of pi over 2? It's, cosine of pi over 2. Cosine is what? The horizontal coordinate? I got to think here. Cosine of pi over 2. At 90 degrees, the cosine, all of a sudden I'm having trouble picturing this. At 90 degrees, the cosine should be 0. Okay, it looks like I'm going to have to redo that one because I've got I don't know what I have here. I got to think this through. The sine of 90 degrees should be 1. So that should be -1. Oh, yeah. Okay, I see it now. What's the cosine of 90 degrees? 0. What's 1 minus 0? 1. What's the sine of 90 degrees? 1. And because it's a negative, it's -1. So we have 1 times -1. And then over here, cosine of 90, 0. 1 plus 0 is 1. Sine of 90, 1. 1 times 1. And then on the bottom, cosine of 90 is 0. 1 minus 0 is 1. And 1 squared is 1. So we wind up with -1 minus 1 over 1, which is -2 over 1. So there is the derivative at 90 degrees. But that's just the beginning of the problem. What they want to know is, what's the equation of the tangent line? Okay, so now you do this, you set up, you say, all right, slope is -2. So we have the equation y equals -2x plus b. Now plug in your point, and here's your whole point up here. Plug in pi over 2 for x, plug in 1 for y. You can see that we get, when you work it out, b equals 1 plus pi. So you put it all together, and there's the equation of the tangent line. So a problem like that has a number of steps, any one of which, you could get tripped up on. That would be a good problem. Again, a really good problem to concentrate in on with your study. Questions? All right. The next section. Oh, yes. This is another thing we did in this chapter. It says find the second derivative. Of course, if you're going to find the second derivative, then you first have to find the first derivative. Okay, so let's do number 50. H of t equals 10 cosine t minus 15 sine t. So what's the first derivative? Well, constant you don't do anything with, 10. The derivative of the cosine is minus the sine. So if you take that minus times 10, you get this minus. So that's that part. And on the second part, again, leave the constant alone. What's the derivative of the sine? The cosine. So there's our derivative. Now we got to take the second derivative. So what's the derivative of the first derivative? Again, leave the constant be. The derivative of the sine is the cosine. Okay? And on the second term, the derivative of the cosine is minus the sine, which makes this second term positive again. So we have arrived. So it's just a matter of doing two derivatives. Likewise, 49, we've got 49 here. F of theta equals 3 tangent theta. Well, the derivative of the tangent is the secant squared. So, I mean, I want you to be cautious here. Here's the problem with trigonometry. Often with trigonometry, it's this notation. You know that secant squared theta means secant theta quantity squared. That little shortcut can get you in trouble, because now if you want to do the second derivative, you need to think of it this way to really do the next derivative correctly. I'm not sure you would see that if you use this form. Anyway, so now the second derivative, okay, so we got to use the power rule. 2 times 3 is 6. Reduce the power by 1, so then it becomes the secant. But now we got to do the chain rule, because secant theta is our inner function, and what's the derivative of the secant? The secant theta times the tangent of theta. And then finally, we can, what? You know, what's the 6 secant times secant? I mean, these are all multiplied. Secant times secant is secant squared. So, second derivative. Okay, I think we're going to leave. I think, unless there are questions, we will we'll leave this. We'll come back. I'll see you tomorrow, and we'll continue. We're going to have to keep reviewing here. Questions? You guys are so quiet today. All right, I'll see you tomorrow. I hope you have a good day, despite the gloominess outside. Make it positive. And don't wait to start studying for this test. Now is the time. Please get in there and roll your sleeves up and work at this. Thank you.